Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so welcome to our seminar today. Raghu Meka, who we had to force him to cut his trip to Israel short to come here, so we're very delighted that he did make it. Raghu's doing his PhD currently at the University of Texas at Austin under David Zuckerman, and we've seen previous students of Zuckerman here. And he's worked on pseudorandomness and algebraic methods, and today he's going to talk about limit theorems in pseudorandomness and learning theory.
Today I'll talk about limit theorems in pseudorandomness and learning theory. And the first question is, what are invariance principles or limit theorems? And I'll illustrate this by giving a few examples. So the first example is the classical central limit theorem in probability, and it's probably the fundamental theorem from probability. And it says the following: if you have n independent identically distributed random variables, x1 through xn, with finite mean and variance, then after appropriate normalization, the summation of the xi's looks like the standard Gaussian distribution. And here by looks like, I mean that the cumulative density function, or the CDF of the summation of the xi's, approaches the CDF of the standard Gaussian distribution. And the second example is the invariance principle of Mossel, O'Donnell, and Oleshevitz, which says that if you have Boolean function f, which is given as a sign of a real valued polynomial evaluated on its inputs, and there is no variable in the polynomial as influential, then the probability that f evaluates to 1 when the input is chosen uniformly at random from the hypercube is close to the probability that f evaluates to 1 when the input is chosen according to the Gaussian distribution. And this is an invariance principle because what it's saying is the probability that f evaluates to 1 is invariant under the input distribution being random or the hypercube or the Gaussian distribution, or more generally for most reasonable product distributions. And a third, perhaps less well-known example is the discrete central limit theorem. And it says that if you have n independent indicator random variables and the total variance of the summation of the x's is not too small, then the summation of the x's is close in statistical distance to the right binomial distribution. And by the right binomial distribution, I mean the distribution whose mean and variance match the variable we are looking at. And by statistical distance, I just mean the L1 distance between the probability density functions. No, because this is statistical distance, whereas the first one only says closeness and CDF distance. And here you need additional conditions, such as this is only for indicator random variables.
What's an indicator random variable?
It's basically a 0 or 1 random variable. And invariance principles have recently found many applications in computer science, most prominently in hardness of approximation, starting with the work of Mossel, O'Donnell, and Oleshevitz, in computational learning, in voting theory or social choice theory, more or less directly or indirectly in communication complexity, in property testing as well. And my work enhances this picture further by adding applications to pseudorandomness, and we make the bubble for computational learning much bigger. Okay, and so my research focuses on 3 areas. One of them is pseudorandomness, and the main work here concentrates on developing a somewhat reasonably generic framework to get pseudorandom generators from invariance principles or limit theorems. And we use this framework along with the invariance principle for polynomials of Mossel, O'Donnell, and Oleshevitz, or MOO from now on, to get PRGs for polynomial threshold functions. And this is joint work with David Zuckerman. And we use the ideas developed in this work along with a new invariance principle for polytopes that we developed to get PRGs for polytopes. And this is joint work with Harsha and Clivans. And finally, we develop a new, somewhat elementary approach to discrete central limit theorems and use those ideas to get pseudorandom generators for combinatorial shapes. And this is work with Gopalan, Reingold, and Zuckerman. And the second category is learning theory. Here, one of the problems we study is agnostically learning polynomial threshold functions. And we get the first polynomial time algorithm for learning polynomial threshold functions under the uniform distribution, and also make the first progress on a 15-year-old conjecture of Gossman and Lineal. And here we use the invariance principle of mu, as well as we develop a new regularity lemma for polynomial threshold functions, which is of interest on its own. And this is joint work with Harsha and Clivens, and the same results were obtained independently by Diakonikolas, Raghavendra, Sarvadiyo, and Tan. And finally, we use our invariance principle that for polytopes to get agnostic learning algorithms for intersections of half spaces. I'll talk a bit about these applications later on. And finally, some of the results are directly in probability. In particular, we give a new invariance principle for polytopes, which is basically a multivariate generalization of the central limit theorem, and more concretely, the quantitative form of the theorem, or the Berrier-Sen theorem. And the most notable thing about this result, I think, is that the error bound we get is only polylogarithmic in the number of constraints, whereas all previous results had at least a linear bound in the number of constraints. And we also developed a new approach to prove discrete central limit theorems from classical central limit theorems. And in this talk, I'll talk about our result for on PRGs for polynomial threshold functions, and I'll describe the construction and analysis for half spaces, and I'll also describe our result of our invariance principle of polytopes and describe some of its applications. So let's begin with the first part.
Before you begin, can I ask you a question?
Yeah.
So why, can you give like a little bit of a motivation? Why are we interested in PRGs that are respect of very specific class of functions?
Mainly because, first of all, we believe that BPP equals P and that there exist good pseudorandom generators, but it's been difficult to construct unconditional generators for all classes, and most of the work in this area is concentrating on specific classes. And besides a natural quotient complexity theory, these specific classes, if you do construct PRGs, you get some nice algorithmic applications as well. Okay.
Which you will mention?
I'll mention some of them, but not too much. Yeah. So the main object here we'll look at is polynomial threshold functions. These are Boolean functions which take n bits as input and output the sign of a real valued multivariate polynomial evaluated on the inputs. For instance, the figure here shows a paraboloid, which is a degree 2 curve, and all the points inside the paraboloid would be labeled positive and all the points outside would be labeled negative. And polynomial threshold functions, or PTFs from now on, have had important applications in complexity theory, learning theory, voting theory, and in quantum computing. Of particular interest are the degree 1 polynomial threshold functions, also known as half spaces or linear threshold functions. And these are Boolean functions which are basically given as the sign of an affine function evaluated on the inputs. And geometrically, we have a hyperplane in n dimensions, and all the points on one side are labeled positive and all the points on the opposite side are labeled negative. And if you're a discrete person, this is what the figure looks like. You have the hypercube and hyperplane which slices the hypercube. Half spaces have been particularly useful in learning theory, in particular in development of important tools such as perceptrons, boosting, support vector machines, and more. And the main question we ask here is if we can construct good pseudorandom generators for polynomial threshold functions. What we want is a function g which takes a few bits of randomness and outputs many bits of randomness which will fool any polynomial threshold function. And besides being an important question in complexity theory on its own, such PRGs would have very nice algorithmic applications such as explicit constructions of Johnson-Lindner-Strauss lemma or Johnson-Lindner-Strauss families, and de-randomizing the randomized rounding algorithms of several prominent algorithms such as the Gomez-Williamson algorithm.
What is the degree that needs in both these applications?
Degree 2 would suffice, but degree 2 would suffice directly, but even if you solve the degree 1 case, you can do some other reductions to solve the problems.
So linear threshold, it's enough to do it for linear threshold functions?
Basically, like for linear threshold, you need very good error, then you can translate. For degree 2, you get somewhat reasonable error, you can get something non-trivial.
Can you always like translate like by blowing up the size quadratically or something like this? Linearize the
what do you mean
the
blowing up the
monomials or
size?
something? Okay, never.
Okay. In this work, we get the first non-trivial answer for this question for degrees greater than 1, and we get significant improvements for the degree 1 case of half spaces. And yeah, and more prominently, perhaps we introduced this technique of using limit theorems in the analysis of pseudorandom generators. And what are PRGs for PTFs? What we really want is a small explicit set of points which preserve the fraction of positive points. So visually, let's say you have a universe of points, such as shown in red here. And what we want is a small explicit set of PRG points shown in blue, such that for any polynomial threshold function, such as the green shaded region here, the fraction of red points is close to the fraction of blue points. And this has to hold for any cross section you take. And formally, you want a generator G which stretches R bits to N bits and fools degree D PTFs, in the sense that for every PTF f, the probability that f evaluates to 1 when the input is chosen uniformly at random on the hypercube is close to the probability that f evaluates to 1 when the input is chosen according to the generator. Here's a summary of previous results on the problem. As I said before, there are no non-trivial PRGs known for degrees greater than 1. And recently, Diakonikolas et al. Showed that bounded independence fools half spaces, and in particular gave a PRG with seed length roughly log n over epsilon squared. And Rabani and Shpilka constructed hitting sets for half spaces with the almost optimal seed length of log n plus log 1 over epsilon. However, hitting sets are in general weaker than PRGs, and it's difficult to go from one to the other. And finally, Karnoy, Rabani and Shpilka constructed PRGs for spherical caps with a seed length of log n plus O of log squared 1 over epsilon. Spherical caps are basically half spaces, but the input is over the n-dimensional sphere instead of being over the hypercube. And spherical caps are somewhat easier to fool than fooling half spaces over the hypercube. And if you do the latter, that is fool half spaces over the hypercube, you can in fact get a black box reduction to fooling spherical caps.
Is it because the coefficient of the polynomial might be large that it's not that the log space pseudorandom generator doesn't work for this?
Exactly, yes. As in, it will actually work, as I'll show you later, but at least the naive analysis says that it won't work. And in this work, our main result is a PRG for degree D PTFs with a seed length of log n over epsilon to the O of D. And for the degree 1 case of half spaces, we do much better and get a PRG with seed length log n plus log squared 1 over epsilon.
So rather than a multiplicative 1 over epsilon squared, this is
plus log squared 1 over epsilon.
Now there's a syntactic similarity between this and spherical caps, and you said that this implies spherical caps but not the other way around?
Yeah.
Okay.
And we also get similar results for spherical caps. And here's the outline of constructions. At a high level, we follow the approach of diaconical.
The last one, just a consequence of the last but one.
These similar results for spherical caps?
So I don't quite understand. So half spaces is degree 1 polynomial threshold function, right?
Then depends on epsilon and
The-
then log over epsilon.
So
we
that
get
would be log n minus log epsilon, which is log n plus
Oh no,
log
the
1 over
epsilon is
epsilon.
outside the log is only on the
oh, okay.
I see.
Yeah. The epsilon is over outside the log. The parentheses should be. Yeah, I wish it was
He puts
inside.
in parentheses when he means them, yeah.
Okay.
Yeah, I wish the epsilon was inside the log, but we're not there yet. So we follow we'll use the outline of at a high level we'll follow the work of Diakonikolas et al. And we first consider the case of regular polynomial threshold functions. And here we'll use standard tools in de-randomization such as limited independence and hashing. But more importantly, we use the Berry-Essayne theorem to analyze our construction for half spaces, and the invariance principle of mu for low degree polynomials to analyze our construction for PTFs. We then reduce the case of arbitrary PTFs to regular PTFs using regularity lemma for polynomial threshold functions. And this was developed in joint work with Harsha and Clivans, as well as independently by Ben Eliezer, Lovett, and Yadin, and Diaconikolas, Sarvadier, Tan, and Vaughan. And finally, we introduced a simple but powerful technique which we call the monotone trick, which shows that PRGs for log space machines do in fact fool all half spaces. And the first, the construction we look at for regular polynomial threshold functions is a simplification of the heating set construction of Rabbani and Shpilka. However, our approach and this analysis are very different from theirs. And in this talk, I'll focus on our construction for regular half spaces. So what are regular half spaces? Intuitively, a half space is regular if no variable has high influence in the half space. More formally, if you have a weight vector W for the half space, then it is epsilon regular if sum of the fourth powers of the Wi's is much smaller than the L2 norm of the weight vector W. And what it's saying essentially is that no coefficient of the weight vector W is much larger than any other coefficient. And why are regular half spaces interesting for us? It's mainly because if a weight vector W is epsilon regular, then by the central limit theorem, the inner product of W comma X, where X is random over the hypercube, is epsilon close to the standard Gaussian distribution. And this gives us a nice target distribution to aim for when designing the generator. In particular, we only need generator G such that the inner product of W and the output of the generator, it looks like the Gaussian distribution, which in turn is close to the true distribution.
Am I supposed to see that immediately? That's the central limit theorem plus regular implies that? Or is
No, I'll show it to you in the next slide. Okay. But intuitively, this is a high-level picture of why regularity helps us. So to quantify this intuition, we'll use the Berry-Essayne theorem, which says the following. Let's say you have n independent random variables x1 through xn, and x is the sum of these random variables. Moreover, the expectation of each xi is 0, and the total variance of x is 1. And most importantly, the sum of the fourth moments of the xi's is small, say it's at most epsilon squared. Then the Berry-Essayne theorem says that the cumulative density function of x is close to the cumulative density function of standard Gaussian distribution, with a pointwise error of at most epsilon. Yeah?
So normally when I seen the Berry-Essayne theorems, they only go up to the third moment, and I think
Right.
there's a constant factor outside the epsilon. Like, is it really important to go to the fourth moment?
Basically, it's usually stated with the third moments, but there's an absolute value inside. And it's much easier to compute the fourth moments because there's no absolute value, and that's why I'm stating it this way. But you can go from one to the other without any loss in parameters up to a constant. And actually the constant epsilon is like the best current record is like 0.8 or something, and there's a long sequence of works which improves it from 3 to 2.1 or whatever to 0.7 now. And as I said, focus on the fact that the error here depends only on the first four moments, and will crucially exploit this in our analysis.
Could you go from a third moment to a fourth moment? I mean, if you have the third moment, the fourth moment might be infinite.
Well, not that bad, right? Because you can use Cauchy-Schwarz to bound the
And he's got
fourth
the
moment.
variance.
The total variance is bounded, and
He's got the variance bound. So,
you can use the Cauchy-Schwarz to get
right,
the bound. Yeah.
he forgot the variance.
And we'll use the notation that random variable x is close to z if the CDF of x is close to CDF of z pointwise. And an immediate corollary of the Berry-Essayne theorem is that if a weight vector W is epsilon regular, then the inner product of W with a random point on the hypercube is epsilon close to the standard Gaussian distribution.
crucial? It's going to be number 4, or is it some constant moment suffice?
Right, some constant moment suffices, yes. And to describe our construction, for simplicity, I'll illustrate it for the case of majority, where the weight vector is basically the normalized all ones vector. And in this case, if you use the Beria-Sein theorem directly, then for a random point x on the hypercube, the summation of the xi's is close to the standard Gaussian distribution with an error of 1 over square root n. And as I said before, the error depends only on the first 4 moments, and we'll try and exploit that. To this end, let t be a parameter, say it's 1 over epsilon squared, m is n over t, and we'll partition the n input variables x1 through xn into t blocks as follows. The first m variables x1 through xn, we'll put them in block 1. The next m variables will be in block 2, and so on up to block t. And let random variable y1 be the summation of the xi's in block 1, y2 be some of the variables in block 2, and so forth. And observe that the yi's are independent of one another because the xi's themselves are independent of one another. And a simple 2-line calculation shows that the sum of the 4th moments of the yi's is small, and in fact it's at most 6 times epsilon squared. And these are the exact conditions we needed to apply the Beria-Sein theorem. And when we do that, we can conclude that the random variable z is close to the standard Gaussian distribution with an error that is constant times epsilon.
The xi's or only for the yi's?
They're pretty small even for the xi's. In fact, they're much smaller for the xi's. Like for the xi's, if you look at some of the 4th moments, it will be 1 over n.
Actually, z is much closer, right? The distance is 1 over square root n.
Right, yeah. We'll get there in a minute. So this is the summary of the previous slide, and as Amir pointed out, we are getting a much weaker bound here, which is O of epsilon, whereas if you use the Beria-Sein theorem directly to the xi's, we get a bound of 1 over square root n. But the point of this analysis, doing this weaker analysis, is that here we only need weaker assumptions on the xi's. In particular, all we need is that the yi's be independent of one another, and we use some conditions on the first 4 moments of the yi's. And we can ensure this by by generating the xi's so that the different blocks are independent of one another, and within each block the xi's are 4y's independent, so that you preserve the first 4 moments of the yi's. And when you generate the xi's in this manner, the same argument will still work, and the inner product of w comma x bar, where x bar is say generated as here, is close to the standard Gaussian distribution with an error of constant times epsilon, which in turn is close to the true distribution we were aiming for. And the randomness used here is 4 log n, which is the number of bits needed to generate a single 4-wise independent sample, times the number of blocks t. So the total randomness used is 4 log n over epsilon squared. And it's natural to ask if we can generalize this approach to all regular half spaces instead of just the majority. However, there's a problem, as even if a weight vector is regular, it could still be skewed towards one block. For instance, the weight vector could be uniform over the first m variables and zeros everywhere else. And to solve this problem, we use an idea of Rabbani and Spilker and do the partitioning into blocks at random. And when we do that, you can reduce the analysis to the case of majorities. And moreover, it suffices to use pairwise independent hash functions to do the partitioning so that you don't use too much randomness. And I'm pushing some of the details under the rug, but eventually you get a PRG for regular half spaces with a seed length of log n over epsilon squared.
Just to understand this particular slide. So regularity in general meant all the coefficients are roughly the same, but even within regular, you're saying the analysis for the majority was perfect regularity,
right.
And to extend it, you need to consider a little bit of variance.
So we saw the
How difficult is what you swept under the rug here? Is it sort of something you can explain in 10 minutes, an hour, 5 hours?
No, it's like 5 minutes thing, but it's just some minor issues you need to take care of. but it's not that big. And so we saw the first part, which is constructing PRG for regular Halfspaces, and then we reduced the case of arbitrary Halfspaces to regular Halfspaces using regularity lemma Sarvadio and Diaconicola's et al., which essentially says that every half-space is either regular, in which case we use the earlier analysis, or it depends only on a few variables, in which case we can fool those by using bounded independence. Okay. And when we do that, you get a PRG for half-spaces with a seed length of basically log n over epsilon squared. And before going further about half-spaces, let me say a couple of words about how to fool general low-degree polynomial threshold functions. So the high-level approach is the same as for half-spaces, in that we first look at regular polynomial threshold functions. We use the same generator, where instead of using 4 wise independence in each block, we use 4 d wise independence, where d is the degree of the threshold function you're trying to fool. And instead of using the Berry-Essén theorem to analyze the construction, we use the invariance principle of mu.
Monomials involving variables from
Right,
blocks.
right. So you need to do a lot more work. In particular, like the analysis turns out to be much more complicated, and we cannot use the invariance principle as a black box. For the case of half-spaces, all we cared about was the statement of the Berry-Essén theorem. We didn't look at the proof of the Berry-Essén theorem, but for low-degree PTS, we actually need to dig into the proof and adapt it to our generator by using a new blockwise hybrid argument. And finally, we reduce the case of arbitrary polynomial threshold functions to regular polynomial threshold functions using a regularity lemma, which somewhat more or less says that every polynomial threshold function is either regular or it only depends only on a few variables. And this, as I said before, is joint work with Harsha and Clivans and was also independently discovered by Ben Eliezer, Lovett, and Yadin, and Diaconicolo, Sarvadio, Ton, and Won.
So the idea then is you have a generator that somehow, like, say, XOR of some k-wise independent distribution and your original generator, and then you say, if it depends only on a few variables, the k-wise will take care of it, and if not, your average generator for regular things will take care of it?
Right, as in we could do that, but it turns out that our generator already has this k-wise independence property, so you don't need to do any additional work. Except, as in the regularity lemma for threshold functions is not as clean as the regularity lemma for half-spaces. You in fact end up with some kind of decision tree which has some low depth, and you need to, there's some technicalities which you really need to take care of there.
All the different works come up with the same form of the regularity lemma?
More or less. The parameters are slightly different, like, some have better dependence on the degrees, some have better dependence on epsilon, but eventually end up with a decision tree which has low depth complexity. So you get a PRG for PTS with a seed length of log n over epsilon to the O of d, and for the special case of half spaces, we get a PRG with seed length of log n over roughly log n over epsilon squared. But hey, this is not the dependence on epsilon that I claimed at the very beginning of this slide, and I didn't cheat then, and we'll actually try and improve this now. And we'll do this by using the monotone trick, which essentially says that the PRGs for small space machines of Nissan and Impagliazzo, Nissan, and Vigdesen do in fact fool all half spaces. And this is a simple idea, but it's, I think, quite powerful. And in particular, this was building on this in subsequent work with Gopal and Clivans. We gave the first deterministic approximate counting algorithm for the Sharp-P-Hart problem of counting knapsack solutions.
They were previously only randomized algorithms.
Yeah.
Kind of, so there was like Randall and so on.
There's also the work of Vigoda.
Oh, right, that was also independently done at the same time as us. I should mention that. Yes. And yeah, the randomized algorithms were due to Morris and Sinclair and Dyer. And the basis for the monotone trick are the PRGs for Reed-Vance branching programs. So let me describe them. Here you have a layered directed graph with S vertices per layer, and there are n layers. And every vertex has 2 outgoing edges, one labeled 0, one labeled 1, and the edges always go from one layer to the next. And finally, the final layer has two vertex, one labeled positive and one labeled negative. And given such a graph, it naturally defines a Boolean function wherein, given an input x1 through xn, you traverse the graph according to the input and output the label of the final vertex you reach. And one of the seminal results in complexity theory, I think, is the work of Nissan and Impaglios and Nissan and Vigdesen, who gave PRGs for polynomial with read-once branching programs with a seed length of O of log squared n. And here by PRGs for read-once branching programs are defined naturally. That is, you want a generator G which stretches R bits to N bits and fools all width s, length n read-once branching programs. And why are we looking at ROBPs in the context of fooling half spaces? The reason is that half spaces can be computed by read-once branching programs in a natural way. We can construct a branching program by looking at the partial sums. We first start with this, the starting state, say, corresponds to the sum being 0. We read input bit x1 and move to the state which corresponds to the value of w1 x1. Read input bit x2, move to a state corresponding to the partial sum of value of w1 x1 plus w2 x2, and so on. And given this observation, it's natural to ask if we can use the PRGs for read-once branching programs to fool half spaces. And the straightforward answer is no, because the branching program we constructed here can have exponentially large width. And why is that?
I don't understand the weights, because you will have to do some arithmetic calculations here.
Right.
And the graphs, you didn't before have weights, you just had sort of a flow which made binary decisions along these graphs.
Right, the edges don't have weights, but basically think of the states as numbers. And the edge from here goes to the number w1 x1 plus w2 x2.
So the number of vertices on these lines are now sort of infinite is the best way to think of it.
Right.
I mean, if these weights are integers between 0 and x, then it's between 0 and n times x. Like the sum can be...
Right, yeah. If they are integers between 0 and x, then you're okay, but otherwise...
minus mx to plus mx or something like that.
Right, that's exactly the problem, because there can be an exponential number of partial sums possible, and you need to have a state for every one of those partial sums. So even though this is a branching program, it's not very good for the purpose of constructing PRGs because it has very large width.
Width is the length of each
Right, width is the number of states in a layer. And our answer to the question is, in fact, you can use the PRGs for read-once branching programs. Why? Because even though this branching program has seemingly exponentially large width, it has a very nice structural property that we call monotonicity, and we exploit that. So let me now describe monotone ROBPs. So we had the branching program from earlier slide for computing half spaces. And now let's set up some notation. Given a vertex v, let a of v denote the set of suffix strings which lead to an accepting state when you start from the vertex v. And let's order the vertices in each layer by the partial sums that they correspond to. For instance, you'll start from minus n times x all the way up to nx at the bottom. And observe that if in this ordering a vertex v1 is less than a vertex v2, then the set of accepting strings from v1 is contained in the set of accepting strings from v2. Why is that? You start from a partial sum and say you end up at an accepting state. Then you should also end up at an accepting state if you start from a higher partial sum, because you're only looking at a threshold. And the same property holds for every layer. And whenever there exists an ordering so that the set of accepting strings from a nice sequence of nested sets, we call the branching program monotone read-once branching program. And monotone read-once branching programs are interesting because we show that PRGs for small width read-once branching programs fool arbitrary width monotone read-once branching programs. That is, in particular, if a generator G fools width 2 n over epsilon width ROBPs with, say, error delta, then it will fool all monotone read-once branching programs, irrespective of the width, with error epsilon plus delta. And as an immediate corollary, you get that the PRGs of Nissan and INW do fool all half spaces with seed length O of log squared n, and error that is 1 over that is polynomially small. And this already improves previous constructions, especially for small errors.
So you have to show some approximation. So what do you show? That for every distribution, you can approximate a monotone program up to epsilon error within by using this match width.
Right. We basically essentially that, but we
like a probabilistic construction that on every input makes a mistake only with probability at most epsilon. Like
we do a simpler property, which is basically you could do that, but it's simpler to construct sandwiching programs. So what we do is use the observation probably first due to Badzi that to show such a result, it is enough to construct approximating programs for monotone read-once branching programs, which are small width, and sandwich your monotone read-once branching program. Right? And
so is that it sort of reminds me of how's it called, sampling from the past or so, where it in principle always works, but you would have exponentially many paths to follow. Whereas if you have more
coupling
from the past,
you know, the Propolis.
Whereas if you have sort of a partial ordering,
like,
then
yes.
you can do it sort of in polynomial time, because.
right, yeah.
So is that a similar argument?
I think so. As in, at least at the high level, it seems similar, but I don't know the details of the coupling thing. But I think it's similar spirit, similar in spirit. Yeah.
How so this particular thing does need the polynomial characterization of fooling and so on and so forth, is it, or can you argue it by just simple combinatorial things? The implication above.
The implication above, as in, I think the argument is simple and combinatorial, and we'll basically show this by constructing, by exhibiting the existence of sandwiching programs. And we'll show that there exist sandwiching programs by actually constructing them.
The sandwiching program is just you discretize. You have the you just put some
right, exactly.
You discretize a bunch of other like a bunch of contiguous states into one state. And
yeah, exactly. I'll show that to you in a minute.
Yeah, that really does look like coupling from the past, and that was also the basis for some of those other works that were mentioned, the Randall work and the Vigoda work.
I see.
They use the coupling from the past in the sandwiching argument.
There's nothing about the past here. The thing is, sort of monotone coupling arguments predated coupling from the past.
That's true.
It's the past part that made that special.
That's true. Yes.
So here, as Boaz pointed out, the intuition for constructing the small width branching programs is that we have a natural ordering of the states in every layer, and we only need to know the states where there is a significant difference in the accepting sets, because they're all contained in a nice nested sequence. And the first approach probably would be to try and approximate the partial sums, but that turns out not to work. But instead, what we do is split the possible partial sums into ranges of intervals. So to this end, we'll pick representative vertices Vs1, Vs2, so on through Vsk, starting from the first vertex and ending at the last vertex. And each of these points will split the range into intervals. And we'll do that so that the probability of accepting from Vs2 is not much more than the probability of accepting from Vs1. And the probability of accepting from Vs3 is not much more than that of Vs2, and so forth. And we do this for every layer. Probability under the original distribution. And because it's a monotone thing, all these probabilities from a nice increasing sequence, and the maximum difference can be at most 1. So the number of points you need is basically at most 2n over epsilon. And these vertices will be our final states in the sandwiching programs we'll construct.
Now if you round up, you get an upper
Right.
sandwich if you want.
Right. So now say we know these representative vertices, how do we draw the edges? And it's very natural. Say we have an edge in the original graph as the one shown here. Then to compute the upper sandwiching program, we round the edge to the next highest representative vertex. And to get the lower sandwiching program, we round to the next lowest representative vertex. Oh, yeah. Okay. Yeah, who says up is up, right? All right. And then once you have this construction, then as in showing that this is actually sandwiching and approximating is straightforward. In particular, every black path is sandwiched between the corresponding blue and orange paths. That shows the sandwiching property. And the error per layer due to rounding is at most epsilon over 2n. So the total error is at most epsilon over 2.
It's interesting if you don't round the sums themselves, but rather
Right.
accept it for waveforms.
Right, as in rounding by sums actually does not work, and that's kind of the only subtle issue here that you really need to think about.
So here it's nice, so you forget you don't try to make the weights integer, small or anything.
Right.
You don't care. You just care about the probabilities.
And that's why the abstraction in terms of Riemann branching programs helps, I think, instead of thinking in terms of weights. So here's the summary for half spaces. We have the PRG for regular half spaces. We have the reduction of the arbitrary case to regular case. And then we had the third thing, which was the monotone trick to show that PRGs for ROBPs work for half spaces. And all of these three pieces fit very nicely together to give our final result, which is a PRG with seed length log n plus log squared 1 over epsilon. And the improvement in epsilon mainly comes from the monotone trick, but you need to use everything together.
Log square 1 over epsilon.
Right, yeah.
Because you cut into blocks.
We cut into blocks, and the number of layers corresponds to the number of blocks, which was 1 over epsilon, so it gives us log squared 1 over epsilon. Right, so this was the high-level outline of the talk, and we saw the first part. Now let's move on to the second part, which is an invariance principle for polytopes. How many minutes?
15.
Okay, that's good. All right.
15 plus epsilon. We'll start a few minutes.
All right. So before going on, let's look at the Berriesian theorem again, but this time in the language of half spaces. So let's say you have a half space F with weight vector W, and the weight vector W is epsilon regular. Then the Berriesian theorem says that the probability that F of L is to 1 under the uniform distribution hypercube is close to this probability under the Gaussian distribution. And once again, this is an invariance principle because it's saying that the probability of acceptance is invariant under the input distribution being hypercube, random or the hypercube or the Gaussian distribution, or more generally for any product distribution. And geometrically, we have a half space in n dimensions, and the Berriesian theorem says that the probability that a random point lies on the positive side under the random uniform distribution of the hypercube is close to the fraction of points that lie on the positive side under the Gaussian distribution. And given this geometric picture, it's natural to ask what happens if you have 2 half spaces, or 3 half spaces, or more generally, if we can have an invariance principle for many half spaces. And this is the exact question we address in our invariance principle for polytopes. So let's say you have a polytope in n dimensions with k bounding faces, and all the points inside the polytope would be labeled positive, all the points outside would be considered negative. And we'll call the polytope regular if every bounding hyperplane of the polytope is epsilon regular. And given this setup, our invariance principle says that the Boolean volume of the polytope, which is just the probability that a random point from the hypercube lies inside the polytope, is close to the Gaussian volume of the polytope, which is the probability that a random point drawn according to the Gaussian distribution lies inside the polytope. And the error is at most polylogarithmic in k, where k is the number of faces, times a factor which depends on the regularity of the bounding hyperplanes.
And if it was k, it would just be union bound, like the version
Right.
with k would just follow from the union.
As in, essentially the union bound.
It's not very clear.
It's not that immediate for sure. but it's much easier than getting this. I'll say a few words about that.
I don't know what a polytope means. So does it have to be bounded?
No, a polytope is basically just an intersection of k constraints.
Okay. So it includes this standard thing as a special case.
Right.
Oh, okay. I didn't realize that either.
Right. We basically have like a set of all points which satisfy some k linear constraints. That's a polytope for us.
It doesn't have to be centered.
It doesn't have to be centered or anything. It's just a k constraints, and
So
that's
you
all.
can take the same polytope, shift it by a little bit, and the bound holds.
Right. As in the bound
You
holds
can
that.
shift it outside the hypercube and the bound holds.
Right. Because even for the Gaussian, it will be nicely concentrated. So if you shift it away, its Gaussian volume also will decrease the same level. And here's our invariance principle restated. And first of all, it's a generalization of the classical central limit theorem, or more concretely, the Berrier-Sein theorem, which corresponds to the k equals 1 case. And the main novelty of our result is the polylogarithmic dependence on the number of faces k. And most previous works gave at least a linear had an error bound which was at least linear in the number of faces. And conceptually, this improves on a union bound barrier because even though most works do not exactly use the union bound argument, essentially what they do is you look at each of the constraints, get some appropriate error, and indirectly end up using a union bound over the different constraints.
Is there an example showing that you need at least some polynomial in log k?
Right. I don't know of an example, but I'm pretty sure that the answer is square root log k. And the reason the square root log k comes is because of there's some connections to convex analysis, convex sets in Gaussian space, and there's this notion of Gaussian surface area. And there the tight bond is square root log k, and that should be the answer, but I don't know how to show it or show any lower bound. And unfortunately, I won't be able to talk in depth or any detail about the proof of this invariance principle, but let me say a couple of words. One of which is that this is much harder than proving a linear in k bound, I think. And intuitively, this is mainly because most proofs of the invariance principles go directly or indirectly via a hybrid argument, where you replace one variable at a time. And when you try and do such an argument in this setting, you incur a loss that is at least linear in k. And our idea is instead to use a random.
Where Mosel got his k or.
Right, yes.
Yeah, okay.
And our idea is to use a randomized blockwise hybrid argument, where instead of replacing one variable at a time, we replace whole blocks of variables, and we do the partition into blocks at random. But when you try and do this, each hybrid step, it becomes much harder to get an error bound, because you're replacing whole block of variables, and you need much greater control on each error step. And we end up using some non-trivial tools from the analysis of Gaussian spaces to actually make this argument work. And instead, I'll talk about a few applications of this invariance principle. And the first application is to bounding the noise sensitivity of polytopes. Given a Boolean function f, the noise sensitivity of f with some error at epsilon is the probability that f changes sign when you take a random point and flip each bit of that random point with independently with some probability epsilon. And geometrically, say you have a polytope, and you draw a random point x, which again say lies outside the polytope. Then the noise sensitivity is the probability that you end up landing inside the polytope when you perturb the original point by flipping each bit with some probability. And using our invariance principle, we show that the noise sensitivity of regular polytopes is at most O of log squared k times epsilon to the 1/6. And this is a significant improvement over the previous best result of Clivans, O'Donnell, and Servedillo, who showed a bond of k times square root epsilon. But their result works for all polytopes, whereas ours is only for regular polytopes.
Is it known that is there an example of a non-regular polytope that has a higher sensitivity?
Oh no, I think the right answer is square root log k again. For all polytopes. The right bound should be square root log k times square root epsilon. And here getting the O of k times square root epsilon is basically they use a union bound across different Halfspaces. And again we beat the union bound here.
Union bound, then it will be immediate, like right? Every Halfspace,
right.
The probability that it didn't flip, you just do a union bound of
right,
it.
right. And why is and how do we do this? Intuitively, this because noise sensitivity is essentially the surface area of the surface you are looking at, because you're just looking at the probability that you cross the surface. And Gaussian surface area turns out to be much easier to handle, and you can compute it by setting up the integration the right way. And we use our invariance principle to translate the Boolean problem to the Gaussian world and use the known result in the Gaussian setting.
So in the Gaussian setting, the answer is square root.
Right. The tight bound is theta of square root log k, and that's why I believe that the invariance principle should also be square root log k. And an immediate application of the bound on noise sensitivity is to learning intersections of Halfspaces. So let's say you have a polytope. The characteristic function of the polytope defines a Boolean function. But the polytope is hidden from us, and the only access we have is to a sequence of examples x1 through xm and their corresponding labels f of x1 through f of xm. And our goal is to compute a predictor for the Boolean function f, which is the characteristic function of the polytope. And our assumption is that the examples are drawn from some underlying distribution D, and the error of the predictor will be measured against the same distribution D. And for the case of intersections of Halfspaces, we'll look at the special case where the input distribution is uniform over the hypercube, and this is particularly interesting for this problem, I think. And using our result on noise sensitivity and known results in learning theory, we get an algorithm for learning intersections of k regular Halfspaces with a runtime of n to the polylog k. In particular, the runtime is quasi-polynomial time when you have polynomial number of Halfspaces. Whereas all previous algorithms had a runtime that was n to the O of k squared, so it's very bad if you have a large number of Halfspaces. And this was true even for highly regular Halfspaces, such as just Halfspaces whose coefficients are plus or minus 1.
Your hypothesis, is it a branching program, PTF?
The hypothesis is going to be a low degree polynomial, which basically comes from the noise sensitivity bound. And this learning theory result also holds with respect to harsh models of noise, such as the agnostic model as well. And the second application is to construct pseudorandom generators for polytopes. So here we want a generator G as before, which stretches r bits to n bits, so that the probability that the output of the generator lies inside the polytope is close to the probability that a random point lies inside the polytope. And the difference we want is that it should be at most delta. And using the invariance principle for polytopes and kind of the generic framework I described for Halfspaces, we combine the two to get a PRG with seed length log n times polylogarithmic in k, where k is the number of faces, times poly 1 over delta. And once again, all previous work results here had at least a linear in k dependence. And a straightforward application of the PRG is to get deterministic approximate counting algorithms for integer programs. So let's say you have an integer program such as the one shown here, which has n variables and k constraints, and you're interested in approximately counting the number of 0-1 solutions to the program. And this directly corresponds to counting the number of integer points inside the associated polytope.
The instance as an input, or do you do it in a black box fashion?
Right, we do it in a black box because you just enumerate over the seeds. But you know, it's interesting even in the non-black box setting, and the only algorithm I know which gets quasi-polynomial time is also black box.
You need things to be sort of the AIs to be nice now because of regularity?
Right, we needed them to be nice. I'll mention that in a bit. And using our PRG, we get the first deterministic approximate counting algorithms for a broad class of integer programs. In particular, we get quasi-polynomial time runtime algorithms for approximately counting solutions to integer programs with regular constraints. And this includes some prominent examples are like contingency tables, dense covering programs, and more. And once again, even for these special cases, the previous algorithms had runtime that was at least exponential in k, whereas we get quasi-polynomial time runtime. And let me now conclude with some future directions for some possible directions for future work. And much of my work involves critical interplay of theorems from probability and in computer science. In particular, it focused on pseudorandomness in learning theory. But I think there's great potential for using these techniques and this correspondence in other areas such as game theory, communication complexity, and other areas in theoretical computer science. And more concretely, you can ask for pseudorandom generators which pull geometric concept classes. Classes such as Halfspaces, polynomial threshold functions, Polytopes, which have a nice geometric interpretation. And an example of this would be there is a rich literature on constructing metric embeddings, and where most of the constructions choose randomness. And it would be great to have explicit constructions for these, not just in terms of complexity theory, but also for algorithmic purposes. And an example of this is the recent work of Ding, Lee, and Perez, who raised the problem of computing the supremum of Gaussian processes, where they use some complicated machinery of measurizing measures to get a constant factor polynomial time approximation. Whereas if you use the PRG for polytopes directly, you get a quasi-polynomial time algorithm, but it gets 1 plus little of 1 approximation, whereas they get a constant factor approximation, which is a universal constant.
So you can get the supremum of Gaussian process, but not cover time.
Right.
Okay.
But this reduction is immediate. Like, you just use the PRG for polytopes and enumerate over the Cs and do a binary search. So it shows that it's interesting for algorithms as well. And one of the central challenges in learning theory is to develop algorithms which are tolerant to noise, such as the agnostic model, such as those that work in the agnostic model. And here, one of the benchmarks is devising algorithms for learning intersections of Halfspaces, even under special distributions such as the uniform distribution of the hypercube. And another interesting aspect is that most known approaches for agnostic learning go via polynomial approximation. That is, you look at low degree polynomials or sparse polynomials or some other polynomials. So it's always just polynomials. So we should really think about some other technique which is non-polynomials. Thank you.
The previous slide that you was just before this. You had game series there? No, that one. The one that
The
you
future
just
direction.
opened up. The last real slide.
Oh, okay.
That one.
Game theory.
What do you have in mind for game theory? What kind of application?
So there's this work by Diakonikolas and Papadimitriou, who have two works actually. One is on computing equilibria in two-strategy anonymous games, and approximately computing equilibria in constant number of strategies anonymous games. And there, if you look at their papers, their analysis, they essentially end up using the discrete central limit theorems. Daskalak, what did I say? Huh?
Daskalak. You said diaconic.
Oh, I see. Okay. Daskalak, okay, Costas and Papadimitriou. And if you like using our approach to discrete central limit theorem, and if you look at the arguments that we use in our PRG for combinatorial shapes, we actually simplify some of their arguments, but it's still not quite there because their argument was really complicated in that and non-trivial, and there should be a more black box way of using the discrete central limit theorem, I think. And in communication complexity, there's recent work by Amit Chakrabarty and Oded Regev, where they indirectly use an invariance principle to translate the Boolean problem to the Gaussian problem and solve the Gaussian problem.